Everything is set up and we are good to go. Alright, well, welcome back to our mathematics library. I've been doing a lot of this recently, and I think I'm going to continue on with some more encryption stuff for a little bit until I figure out I want to move on to something else. But for now, I think I'm good with just doing this. Might do some OpenGL in a bit, but I have some more hash functions for us today. We are going to be looking at the predecessor to the SHA3, the secure hash algorithm 3 function, and that's just going to be SHA1, and it was one developed in the 90s, so it was a bit earlier than than SHA3. It's a lot simpler, but you will see a lot of similarities between the two. I mean, just for example, you're going to see that there's still that block structure where we process messages in blocks and then pad it at the end, and we're always going to be padding no matter what, even if it's a complete block, and that will be passed into some function that takes in a block and then outputs something else. But the difference is the representation of the block. In SHA1, it's simply just going to be a string. It's not going to be a 3D prism or a 3D rectangle like we had in SHA3. It's just going to be simply a string that looks like this. It's this 64-byte block, and we're simply just going to add on, just process on this block, and we can represent it as a string. Nothing special, because we don't need to do any row rotations or anything specific like that, where you need a cell location, essentially. Alright, so once again, just a quick recap of hash functions. So I think I had some stuff up here. Yep. Hash functions essentially just take in data and pass it through a function, which is going to be h of x, and it outputs some other value that is in a finite set. So we use the example of hash tables, where you pass in some data and it has a numerical value, and then you're going to get an index. And one example would just be a modulo function, so you take the modular reduction. And then for encryption, it's a little more complicated because you want to make this function irreversible. Because if we're going to be storing passwords in a database, we don't want to store the actual passwords in the database, because if someone breached the database, they would have access to all the passwords. So what databases do is they'll store hashes of these passwords, and these hashes are generated using one-way functions, which means that you can't go the other way. So if with the hash we can't go back to the password, that's essentially what this illustrates right here. So in encryption, once again, we're gonna take the hash of a password, store the hash. So if anyone were to gain access to the database, they would just have a bunch of hashes, which they would not be able to obtain the actual passwords from. Alright, so let's go back over here, and we're going to talk now about SHA1. So, like I said before, it's going to be very similar to SHA3, or the high-level structure at least. We're going to go through some pre-processing of the whole message itself, then we're going to divide it up into blocks and process each block individually. So we're going to be using 512-bit or 64-byte blocks. There are no extra parameters. Like with SHA3, we had a bunch of parameters for Ketchak. We had the L, which kind of derived a few other parameters, and then we also had R, which was based upon the security level. But with SHA1, there are no parameters that you can control. It's just the set values that are already existent in the algorithm. Alright, so I'll just talk about, let me actually just insert a space right here. Alright, so let's say we have our message here. This is MSG, goes from 0 to n bytes long. The way we're going to process this is, like in SHA3, we have to add some padding at the end. The padding is a lot simpler. We don't have to do any bitwise XORs. you're going to see why that's just in the code representation too, but it's also just, we simply just have to add a singular bit of 1 and then a bunch of zeros after that. Like so, until we get to some value that is a multiple of 512, or we're going to pad zeros until we get to a multiple of 512. So k times 512. This is n bits, sorry, n bits. So we're going to be padding until we get to a multiple of 512 bits, or 64 bytes. Now the reason why I drew this extra box here is the last 64 bits, or 64 bits. So this right here, 64 bits. So this is going to be k times 512 minus 64. These last 64 bits are going to be reserved for the size of the message. So it's going to be n. And that's also in bits. So for example, if we had our message, which was this string of characters right here in bytes, this is just going to be the character A, B, C, D, E. We have that these 5 characters are input in, so we have 61, which is A, 62, so A, B, C, D, E, and then after this, so we have 5 bytes in there, and the rest of this is just going to be padding. So the 0x80, this in binary right here, this is just going to be 0x80 is going to be 1, or I'll just say in binary it's 0b1, bunch of zeros, and we're going to pad it to the end. So we're padding it to the end of the block here, which is now 512 bytes, or 512 bits. And then these last 8 bytes here, these last 64 bits, are going to be reserved for the length of the message. So that's equal to n, which was, that's going to be 5 times 8 is 40 bits. So 40 bits, which is equivalent to 0x28 in hexadecimal, which is what we have right here. So yeah, the padding scheme is pretty simple, and we'll look at how to do this in the code. And there will be one corner case that we'll have to look at, like if we're at a complete block and then we need to pad an extra. Like even if we were to pad this 0 right here, like if that 8 was over here, we would have to go to another block because we don't have 64 bits for the length. So we need to have a full 64 bits at the end of the whole message. Or at the end of the last block for the length of the message. Alright, so I'll give you a little bit of a high level description now. Now that we know the padding scheme. So once we have passed the message through padded, so we pad the message, make sure it's all good. And then we're going to start going through our iterations here. So now we need to break it up into blocks. So M1, M2, all the way down to MN. So once again, the padding here, it's going to be the message, then ones with a bunch of zeros, then the length. And this is some multiple of 512. Now each of these message blocks are going to be 512 bits. So it's so if we had a message that was like that was 90 characters, that would be more than one block. So we would have a complete block which was just the message. So if we had so this is, I'm gonna write it in, or you know, I'll just do this. Where's our calculator? Here. 90 times 8, 720. So this whole thing was 720 bits, and I'll actually just get that in hex right now so I can write it down. 0x2d0. So 2d0 is the length, that's n, pad, MSG. So we have 720 bit message. And so what we're going to do is we're going to take the first 512 bits of this whole of the padded message and pass that in for one round. So this becomes M1. And then the last 512 bits, which gets us to 1024 bits, becomes M2. So the second block will actually have the padding and the length inside of it. So we pass each of these message blocks through the round of SHA1, and in each round we're going to be updating 5 different factors. So initially, so these are going to be the 5 factors that we're going to be updating, in which will eventually determine the output, the hash, or the digest of the algorithm. They have these initial values here in hexadecimal. So these are all hexadecimal. These are 4-byte words or integers. And then what we're going to do is, after each round, we're going to be adding some value to these constants. And then after MN, we have H0, H1, H2, H3, H4 determines the hash. So I'll call the function that SHA1 actually executes as just f. Kind of like catch-check f, but this one doesn't have a special name for it. At least not that I know of. So this is, in essence, this is the high-level description of SHA1. Let me just clean this up a bit. And then this is our digest right here. I can actually get a better marker. So that's the output, the H0, H1, H2, H3, H4. That's the output. All right, so let's actually look into what this SHA1F is. So I already told you guys what the initial values of the constants are. So these initial values these are the initial values of the H constants. And then we have a few other things. I'll actually just drag this over here, because this has more to do with this. These two are more related than to the H constants. These are going to be actual constants and functions that we use in each round. So as with SHA3 or catch-check, the SHA1F is round based as well. It has 80 rounds, 80. And for each kind of segment, the functions will differ based on what round it is. So in each block of 20 rounds, we'll use a certain round constant, round function pair. So from 0 to 20, we have the top one here, then we have 20 to 40, second one, 40 to 60, and then 60 to 80. And once again, these are also hexadecimal integers. And then we will also have these functions, which are dependent, once again, on what round it is. So, for the actual description of the algorithm itself, this is what I got from the NIST document from 1993. Or wait, this supersedes that. This is 1995. So once again, this step A was just dividing it up into, oh no, sorry, that's not right. We have already done this stuff here. So we have processed each we have pre-processed each block of each message block. So now to process each of those blocks, like through and put them through the SHA algorithm, we're first going to divide the message up into 16 words, and these are going to be 16 4-byte words. So we'll have an array called W, which is an integer array of length 16. Here in this first version of it, it wants us to have the array as of length 80, which is a lot, but we will be kind of getting around that with some more computation. So essentially we initialize all the W values. This may be similar to the AES key function, where we take W, or we have just like a massive table of keys for a key schedule, and it's going to be a little similar to that, where we pre-process this. That's the this iterate, or this version right here will pre-process those the W constants. But all you need to know is that for each round from 0 to 80 has its own constant. So you can consider the W here like round constants. All right. Now for step C here, we initialize our some 5 other integers, A through E, and then we do our 80 rounds. And in each round, we're gonna calculate a temporary integer, which takes a shifted value. We call the round specific function T, or F. So this and this function F and the constant K are dependent on the round value. So 0 to 19, 20 to 39, 40 to 59, and then 60 to 79. That's dependent on, or whichever section we're in right now, that will determine these two. Now for W, that's just the round constants that we pre-computed. And then we essentially just do a few other computations. We do some swapping, or not swapping, but we just move some values around, set E to D, D becomes C, C becomes the shifted value of B. This is a circular shift, by the way, the S here. B becomes A, and then A becomes a temporary value that we calculated. And then after all the iterations, we update the H values. Just by adding A through E to the corresponding ones. So notice how at the beginning we set A to the H constants. We set A through E to the H constants, no matter what they were. And then after the iterations, we're adding A through E to the H constants. And then in the next block, we're gonna continue using those H values, and we're not gonna revert back to the originals. We're gonna keep the H values in each block. And then once again, after we're done processing the last block, the output will just be H0 through H4 just concatenated. Now, you might not want to. The only downside here would be having this 80 word array. Like, who the fuck wants to do that? So what you could do is you can implement a circular array. You might have seen something like this if you took a comp sci class and you learned about circular queues or something of that nature, which could definitely be helpful, because you notice here how we're only accessing the last 16 values of W to calculate every round constant after setting the initial values. Well, in that case, we could just keep the array and just kind of rotate it through every 80 values. So think about, so here we have so 0, 1, 2, 3, 4, 5, 6, all the way up to 79. That's the 80 word array. And then now for a circular array, it's going to be 16 values in a circle. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 15. So the initial 16 values will just be the input block that we pass in. And then as we go through each iteration, we're going to move it up. So 0 becomes W at 16, then 17, 18, 19, 20, and so on and so forth. And we're going to continue doing that until we have each of the constants. But the fact is, to calculate W at 16, we only need the last 16 values. So W at 16, we're only going to need W at t minus 3, which is going to be 13. W at t minus 8, which is just 8 right here. W at t minus 14, which is 2. And then W at t minus 16, which is going to be 0. So we need the value that's currently at the place that we want to overwrite, along with a few other values. But essentially everything else is the same. So instead of having t as our index, we just take it mod 16. So we get a valid index in the circular array. And then to get the values at the array, we're going to do another mod 16. That's what the bitwise and what the mask is, because the mask is just 0xf, which is equal to 15. But everything else is the same. And then we're going to index into W using the reduced index. And also notice here how we're going to be adding to get an index. You could also subtract, but adding is just the way they have it here. So I'll do that. And it works just as well, because if you add or subtract a value, you're still going to get the same reduction. But so s plus 13. S plus 13 is equivalent to s minus 3 modulo 16. Like for example, if we had s is equal to, let me just zoom in here so I can show you guys this. S is equal to 4. And we do s minus 3 modulo 16. That's 1, and then we have s plus 13 modulo 16. That's also 1, because s plus 13 is going to be 17, and s minus 3 is just going to be 1. So there's 16 numbers apart. So as a result, you're going to be getting the same modular reduction. So yeah, that is pretty much SHA1 high level and then low level. Which is simple. It honestly is as simple as it seems. It's not too complex, and when we write the code, it's going to be a lot shorter than SHA3, especially the pre-processing part. Alright, so let's hop into our code here, and we're going to start with our header file. SHA1.h and SHA1.c. Now before I forget, I'm going to, what did I just do? I'm going to want to add SHA1.c to the build path, because I forgot to do that last time and I almost screwed myself over. Where is it? Alright, so debug and run. Those batch files are now updated. Alright, so let's hop into the header file. Let me pull up my reference, and we're all good. Alright, so we'll start by including cmathematics.h, as we do. Then we're going to do our macros, if not defined, SHA1H, define SHA1H, and then endif. We're going to have a few macros here, because once again, we're just going to define the parameters, the set parameters for SHA1. These are not, you can't change these. So we're going to define SHA1 out. Let me actually just change something real quick in SHA3. Notice this when I was looking over the code. I just had a macro name mismatch where I had, if not defined SHA3 capital H, define SHA3 lowercase h. So that would just lead to some bad stuff. We don't want that. Alright, so for our macros, define SHA1 out. It's just gonna be the output size. So I'm gonna say 160 right shifted by 3. That's just I didn't mention this, I guess. SHA1 outputs blocks of 160 bytes, or bits rather, which is just going to be 160 divided by 8 bytes, which is the equivalent of 5 integers, because 160 divided by 8 is 20, which is 5 4-byte words right there. Alright, then we're going to have define SHA1 number of rounds as 80 for the number of rounds, and then define SHA1 block length is 64. Alright, so those are the macros that we need. Now we're going to do some constants, just like we had for SHA3. So it's going to be the same kind of format, where we just have some externs here to help with storing some values. All it's going to be is just an extern unsigned integer SHA1H, so these are going to be the initial H values, and it's going to be an integer array of length 5, and then extern unsigned integer SHA1 round constant 4. So there's going to be 4 of those, and these are going to be our K values. So these ones right here. Alright, so constants. Alright, so I'm now going to introduce something new that we didn't look at with SHA3, and it's going to be the context structure. So with SHA3, we essentially just had one function to do it all. You called SHA3 hash, you pass in the whole message as is, and it did it all for you in that one function. Typically what you'll see in cryptography libraries is you're going to want to initialize a context, and you can progressively add more text to the state, to the context. So if you wanted to add it in different batches, you could do that. Like if you had, if you wanted to concatenate messages, you could do that in 2 rounds, and it wouldn't affect it because you're only going to be running the catch-f function when you have a complete block. So you could progressively add it until you get a complete block, and then once you get that complete block, you can then run the catch-check function, and then you don't have to take the output until you're done adding stuff into the message. I already have that implemented on my side. I'm going to be uploading it to GitHub once I document it, but it's just going to be a more standard way to do that, because sometimes you might want to concatenate strings and pass them into SHA-3, but you don't always want to create a new string to concatenate. You just want to pass two different strings in consecutively, and it'll do the same job. All right, so the way we're going to represent this is through a structure. So we're going to say type def struct SHA1 context, and then we'll just call it SHA1 context. And in here, we're going to have an unsigned long message length. So that's going to be the existing message length. Why do I use an unsigned long? Well, if you remember, that n here, the last value that we pad the message with, is 64 bits. And luckily, C already has a type for that, which is the long. All right, then we're going to have our constants, unsigned integer h of length 5. This is going to be I don't know exactly what to call this. It might be something that we can call it. This is just a buffer for the output. So these are the h values. All right, and then we're going to have our state values. So we'll have a cursor, so integer state cursor. And once again, this is just going to be the cursor within the state, so we can progressively add until we get a complete block. Or add and run, just so we can keep track of where we are. And then we're going to have an unsigned character state, and that's just an array of length SHA1 block length. And look at this. Look at how simple the state is. Instead of being a 2D array of unsigned longs, it's simply just a string. It's a byte array. So that's all this context is going to be. It's just going to have the message length, the progressive message length that we can add to, the buffer for the output, and then the state values. Okay, let's actually go ahead and define our state constants, or the SHA1 constants right now, just so I can get that out of the way. So in SHA1.c, just make sure to include SHA1.h, and then I'll also do the other includes right now. We're going to include string.h, include stdio.h, and include standardlib.h. All right. Now for our values, for the h values, I'm just going to tell you them. I probably should have created a paste bin, but I can just put it in the comments somewhere. So for h, it's going to be 0x, and the first value is 674, this is in hexadecimal, 674-52301. Value number 2 is 0x EFCD A889. Then 0x98B ADCFE. Then we have 0x10325476. And then finally 0xC3DE1F0. Oh, sorry. C3D2E1F0. Let me just verify these values real quick. 674-52301 EFCDAB89, not 889. Misread that. That's good. I don't know why I'm saying these aloud. there's a link to this document down below, but I'll also put it in the comments somewhere. So, and the third one is 98BADCFE. Third one is 103254766, and then finally C3D2E1F0. These seem very random, I'm not gonna lie. And then now for the round constants, so these are gonna be the K values. So I'll honestly just change this name to SHA3 or SHA1K. Because it's more consistent with the documentation. So it's going to be 0x5A 82799. Then 0x6ED9EBA1. Then for the third one, it's 0x8F1BBCDC. And then finally 0xCA62C1D6. And I'll just verify these. 5A827999, 6ED9EBA1, 8F1BBCDC, and then CA62C1D6. Alright, so that was a long-winded way of saying copy and paste that from somewhere. Don't listen to me. Alright, let's do our utility functions. As with SHA-3, we're going to have a rotate word function. It's going to return an unsigned integer this time instead of an unsigned long. So it's unsigned integer SHA1 rotate word. Takes in an unsigned integer w and an unsigned integer d for the number of spaces to shift. And then the second one will be void SHA1 reset state, which takes in a pointer to a SHA1 context. And this will just clear the values in the context. Alright, so let's pass over these values. For the signatures, for rotate word, I realized that I'm actually going to do this right now. For SHA3.C, the rotate function, I just overcomplicated this. You simply, all you have to do is reduce the number of spaces to rotate by, and then all you have to do after that is simply return in parentheses w left shifted by d, bitwise ORed with w right shifted by. Then for the unsigned long, it's going to be 64 minus d. And then for the unsigned integer, it will be 32 minus d. I was busy jerking myself off using masks and shit, but this is all it is pretty much. It's much simpler. You just left shift the part that you want to put in the front, and then right shift the part that you want to put in the back. So for SHA1 rotate word, for the integer way, it's going to be, we have to reduce the number of spaces to rotate by, so d bitwise and with 0x1f, which is just modulo 32, and then return in parentheses w left shifted by d, close parentheses, bitwise ORed with w right shifted by 32 minus d, close parentheses. So it's much simpler than I made it seem. Alright, so for reset state, 2 lines. We gotta reset the state cursor, so ctx.stateCursor is equal to 0, and then we gotta set the memory to 0 as well. So memset ctx.state is the destination, the value will be 0, and then the size will be SHA1 block length. We're going to reset the state every time we run the before we run the function, or every time after we run the function, because once we've output the values to the h constants for the context, we don't give a shit about what came before, because we're only going to be adding the output of every round to the h values instead of XORing it with the current state like we did in SHA3. Alright, so back into the header file, and we're going to have 4 more functions. 3 of them will be our context functions, so I'll do those first. So we'll void SHA1 init context, and we'll pass in a SHA1 context pointer. Void SHA1 update. This function will be used to pass in text and data to be processed. So we pass in a SHA1 context pointer, and then we pass in an unsigned character pointer in message, which is the byte array that we want to pass in, and integer for the number of bytes to take in. And then void SHA1 Digest, which is another word for output values. So SHA1 Digest, take in a SHA1 context and take in a reference to a string, so an unsigned character double pointer out. And then for the SHA1 function, it's just going to be void return SHA1 f, and it'll take in an unsigned integer array h of length 5 and an unsigned character array state of length SHA1 block length. So each call to the function requires the state, which is the message, the data that we need to hash, or that we need to hash in this current call, and then the output, which we will add to, which is the h values here. Alright, so let's copy all 4 of those signatures over. And we will start with init context. So we just need to set up the values so that we're ready to read. So we'll start by saying ctx.message length is equal to 0. Then we're going to copy over the initial values of h to our output buffer. So memcopy ctx.h SHA1 h is the source. So that's the extern array that we had, and then the size will be 5 times the size of an unsigned integer. And then we need to reset the state. So SHA1 reset state passed in ctx. So once again, this function will just set the cursor to 0 and then set all the memory to 0 as well. Now for update, this is going to be super simple. We're just going to take bytes until we have none left. It's going to be a while loop. We don't even have to calculate the number of blocks. It's just going to be that simple. Just because we don't have any specific place, any specific cell that we need to stop at, that we need to read to. We don't need to do any calculations to find that cell because we just have the cursor and that's it. But we will have an extra cursor, which is going to be the message cursor. So message cursor is going to be 0, and then we're going to have a while loop. So while message cursor is less than n. So since we're just reading from left to right, we can just use a while loop. We don't need to say for integer I goes from this to this. It doesn't really matter. We just want to read or copy bytes in until we don't have any more. With SHA3, we had to copy bytes in a very specific order. It was a clusterfuck. Like we had to go along the x-axis first, then the y-axis. We had to do some XORing stuff. Here it's just going to be, just a copy function because we're not doing any XORs, so we're just we're overwriting the memory. So we're going to copy bytes, or we first have to calculate how many bytes to copy into the current block. So integer number of bytes in block, we saw this in SHA3, This is going to be equal to the minimum of SHA1 block length minus ctx.state cursor. The minimum of that with the maximum of, or just the minimum of that subtraction and n minus message cursor. So determine if end of block or end of message comes first. And the distance to that, of course, because that's just going to be the number of bytes that we want to read. Alright, then we're going to copy those bytes. So mem copy, destination will be ctx.state plus ctx.state cursor. This is going to be some pointer arithmetic here, just going after the cursor. And the source will be in, the in message plus message cursor, and then number of bytes in the block. So we've copied the bytes, now we want to advance the cursors. Both cursors. So message cursor plus equals number of bytes in the block, and then similarly ctx.state cursor plus equals number of bytes in the block. Now, what's up here? There we go. Now, what if we got to a complete block? Well, we want to call the function, but we need to determine if we actually got to the end of the block, and that's just going to be with the state cursor. So if ctx.state cursor is equal to SHA1 block length, then we reach the end of the block. Call the function. It's simply going to be SHA1f. Two parameters are going to be ctx.h and ctx.state. And then we reset the state. SHA1 reset state passing ctx. So after we call the function, we want to reset all the variables, or not all the variables, just the state variables, because we want a clean slate to write into. Technically, we don't have to set the memory to 0 in the state, because we're just going to be overwriting it either way. You know what? Yeah, let's get rid of this reset state function and just replace all the calls to reset state with just ctx.state cursor equals 0, because it doesn't matter. We don't need to reset the state at all. Resetting the state is just setting the cursor to 0, because we're going to be overwriting it anyways with mem copy. So after we call the function, we just need to say ctx.state cursor is equal to 0. And then after the loop, we've successfully read everything in, and we're going to increase the message length. So ctx.message length plus equals, and we're going to say n left shifted by 3 to go to bits, length in bits. Once again, left shift by 3 is just multiplied by 8. So, yeah. All right, let's do our digest now, which will be when we actually start outputting. So we're going to start by doing our padding. First byte is going to be our first bit 1. All right, so all we have to say here is ctx.state at ctx.state cursor plus plus is equal to 0x80. Now you might be wondering, well, what if this is the last? What if we have an overflow here? Well, we're not going to, because if we ever reach the end of the block through the update method, we're going to reset the state to 0. And then here, we would have to set the rest of the memory to 0, I believe. Is that right? Hold on. Let me think about this real quick. Okay, I think we're, yeah. The only thing we have to check for is when we set this byte is if we have reached the end of the block by setting this byte to 0x80. So all we're going to ask is if ctx.stateCursor is equal to if that's equal to, hold on, I'm trying to think here. Oh, yes, okay. So if the state cursor is greater than or equal to, hold on, I need to figure something out real quick. So we set the first bit to 1 and the rest of the bits to 0. So to set the rest of the bits to 0, we're going to say memset ctx.state plus ctx.stateCursor. Value is going to be 0, and the size will be the maximum of SHA1 block length minus ctx.stateCursor and 0, because this could be a negative value potentially if this is the last byte in the block. So now it won't be a negative value, but just to be a safeguard, because we don't want to be setting negative like that. I don't want to screw around with that memory stuff. But the maximum of this, just to make sure it's always a positive value, or 0 or a positive value, just setting the rest of the bits to 0. Now we want to check, because remember, we're not done with padding, we need to output the size. So if ctx.stateCursor is greater than or equal to SHA1 block length minus, is block length in bits or bytes? It's in bytes. That minus 8, because that's the length, or minus the size of an unsigned long long. Just for readability here. So if that's the case, then we have written into the space reserved for the size, so we need to allocate a whole new block. Even if that one bit, even if we write into this one little space here reserved for the size, then we would have to create a whole new block, because we need 64 bits for the size. So what we're going to do is we're going to call the function SHA1F on ctx.h and ctx.state. Then we need to reset the state, and here we're going to say ctx.stateCursor is equal to 0, and we're also going to reset the memory here because we need a clean block. We're not going to be overwriting it. We need a complete clean block because we're only going to be overwriting the last 64 bits. So memset ctx.state 0, and it's going to be SHA1 block length. Now to set the last we're going to set the last 64 bits. Memcopy is a bit weird because I believe it operates small endian byte-wise and big endian bit-wise. So each byte has the most significant bit on the left, but the most significant byte is on the right side. That's what I've gathered just from trial and error. So what we're gonna have to do is we're gonna have to read in the values in a very specific way. So we're gonna set the last 64 bits as length of message. We're going to get the message length in a temporary value. So unsigned long size is equal to ctx.message length. Then for integer I is equal to 0. Do I need an I actually? No, for integer I is equal to 512 left or right shifted by 3 minus 1. Hold on. Am I doing this right? Yes. So I is equal to the last byte in the state. The condition is just going to be size. And then we're going to say j minus minus. So we're going to walk backwards. So set least significant byte on rightmost slot. And this condition is going to be size because whenever size is 0, we don't have any more bytes to write because everything is already 0. And this will never go beyond 8 bytes because if we continue to, we'll see why, but so we'll write in ctx.state at j, or at I, sorry, is equal to size. This will automatically chop off, this will just get gets least significant byte of long. So by just truncating the other 7 bytes. And then we're going to divide the size. So size, right shift equals by 8. So remove least significant byte. So if we continue to right shift along, it's eventually going to get to 0. Even if it's just all ones, if it's the maximum value, we're going to get to 0 eventually. Because if we continue to right shift out bytes, those 1 values, it's going to be left shifting or it's going to be inputting 0 bytes. So eventually the size will go to 0, and this condition here will result in false. Alright, so we have now padded it properly, and now we can call the function on the last block. So SHA1 function, we pass in ctx.h and ctx.state. We're going to reset the state. For some reason, we just can't. Do we have to? Yes. ctx.state cursor is equal to 0. And then now we're going to output. So the output is just the array ctx.h. That's just the buffer, the output buffer. I'll actually just put a comment here. Yeah, output buffer. So we need to allocate first. So we're going to dereference out because it's a pointer to a string. So that's equal to malloc SHA1 out, the macro, times the size of an unsigned character. And then if not the dereference of out, this is just a memory check we're going to return just to make sure the memory is actually allocated. And then we're going to output. So once again, memcopy and memset work, or memcopy works in a weird way. So we're going to have to do this differently. So we're first going to iterate through each integer normally in the output buffer. So for integer I is equal to 0, I is less than 5, I plus plus. That's just normal stuff. Now with each with memcopy, it was being a little weird, where I was trying to, hold on, let me see this example real quick, because I'll look at the example and I'll know what I was looking at. Yeah, I think it was doing small endian bits, which is really weird, but like the least significant bit was on the left side. I have no fucking clue how it works. I just need to do some trial and error, and I'll try and figure it out at some point. But essentially we need to read in bits or bytes manually. So we're going to do for integer j is equal to 3. We're going to count down. J is greater than or equal to 0. J minus minus. And then we're going to say the dereference of out in parentheses at I times 4 plus j. So we're getting the character is I times 4 plus j. That'll just never go above 20. And this is going to be equal to the character value, the truncated value of ctx.h at I. So it automatically truncates, actually. So we need to get least significant byte. Is that right? Yeah. And then we're gonna remove that byte. So ctx.h at I right shift equals by 8. Remove last byte. And that's it. Well, that's not it, but that's it for the high level description of it. So we essentially just output it, and we'll see how that works. Now for the actual function, the SHA1 function, this is going to be, let's just blow through this real quick. We first have to initialize the state. So not the state, initialize w, the array. So it's going to be an unsigned integer array of length 16. And we're going to, the first 16 values are just going to be the state. So for integer I is equal to 0, I is less than 16, I plus plus. Once again, memcopy was working weird. So this time we're going to say for integer j is equal to 0, j is less than 4, j plus plus. And in order to get, to have like a one-to-one copy, I have no clue why this wasn't working properly, but essentially we have to copy in the bytes manually in order instead of just calling memcopy. So we're going to say w at I, left shift equals by 8. So we're going to increase magnitude by 1 byte. And then say w at I bitwise or equals with state at I times 4 plus j. So copy in a byte. So let me just draw this out real quick, because I think this might need this warrants a description. So let's say we had our byte was 0x, or our first 4 bytes were 3f, 217a, 6c. So that's 4 bytes. And we wanted to input this into an integer to get an integer equals 0x 3f217a 6c. What memcopy would do would give us 0x 6c 7a 213f. So the bytes are still maintained, but it's just the ordering that is screwed up. I'm not sure. I need to do some more trial and error to figure that out. So essentially what we're going to do is we're going to have our integer I is equal to 0, or not I, I'll say w is equal to 0, 0x 0 0, just a bunch of zeros, and then we're going to take our first byte, 3f, so b is equal to 3f, and we are going to bitwise OR that in with w. So w or b is equal to 0x 0 0, because this b, you can think of there are being implicit zeros in front of it, but it's a character, so we don't have them technically. So it's going to be a bunch of zeros and then 3f at the beginning. We just iterate that that's wrong. So then we're going to left shift this by 1. So W left shifted by 8. Or 1 byte, which is equal to 0x, 2 bytes of 0, and then 3f, and then 0, 0. Then we're going to say the B is equal to now 0x21, and we're going to bitwise OR that in. So it's equal to 0x 0, 0, 0, 0, 3f 21. So we're always bitwise ORing with zeros, so we get the actual input there, and so on and so forth. I'm not going to write the rest because it's kind of pointless. You get the gist just from this here. All right, now we're going to have our variables. Initialize function variables. So unsigned integer a is equal to h at 0. And then b, c, d, e are just going to be the next values. So I'm just going to do b, c, D, E, 1, 2, 3, 4. So A through E correspond to H at 0 through 4. And then we have our mask. Or you know, we don't even need a variable for this. We could just, it wouldn't make a difference, yeah. All right, then go through our 80 rounds. So for integer t is equal to 0, t is less than SHA3 number rounds, t++. Then we're going to get the index modulo 15. So integer s is equal to t bitwise and with a 0x 3f. Is that right? Or 0xf, sorry. Mod 15. Or that should be SHA1 number of rounds, my mistake. Alright, then once again we're going to calculate our new values of w only if t is greater than 16 or 15, because we have already set the first 16 values in the array. Now we want to determine, okay, should we put more in? What we're going to say is if t is greater than or equal to 16, then w at s, the reduced index, is equal to SHA1 rotate word. The word to rotate is going to be w at, and I'm just going to say all of these indices are going to be bitwise ANDed with 0xf, just reduced. So it's going to be w at s plus 13. XORed with w at s plus 8, reduced. XORed with w at s plus 2, reduced, and then XORed with w at s, and this value will be shifted by 1. So we want to shift this 1 bit. Alright, so now we're going to calculate our temporary value. So integer t, unsigned integer, TMP is equal to SHA1 rotate word. We're going to rotate A by 5 bits, and then add this to E and W at S. So this corresponds to the temporary value is going to be this over here. So temporary is A shifted plus E plus WS. Now, for the other two factors, the function F and K, those are based on the round number. So we're going to have to do a cascading if statement. So if T is less than 20, then we're going to do our first ones. the first pair. So temporary plus equals SHA1 K at 0, which is just KT, plus then our function, the first function will be, make sure this is all in parentheses. Then we have to open up another set of parentheses, B, bitwise ANDed with C, this bitwise ORed with the complement of B, bitwise ANDed with D. I'll just zoom in so you guys can see this here. So this is the first constant plus the function corresponding to the first round. Now else if t is less than 40, and we don't need a lower bound because we already know it's not less than 20, because otherwise this call would have been executed. Then we're going to say temporary plus equals SHA1 K at 1, the next constant, plus now the function here is just going to be B XORed with C XORed with D. Else if t is less than 60. The third one, temporary plus equals SHA1 K at 2, plus the function here is going to be, it's going to be a little weird. We have 3 bitwise ORs, so it's B and C, ORed with B and D, ORed with C and D. So once again, all of those are going to be bitwise operations. It's just every pair of the 3. And then else, we're going to say temporary plus equals SHA1 K at 3 plus B XORed with C XORed with D, which is the same as the second function right here. Once again, this is a direct translation from the documentation. They wrote it out in pseudocode, so you can just take this and write it in code pretty much. So once again, only one of these blocks will be executed. If t is say 34 or 55, then we want to execute the third pair here. So 55 gets us in, we want k at 2 and f at 2 as well. So 55 is not less than 20, 55 is not less than 40, 55 is less than 60. So we will run the third command here, which is right, but we don't want to run the fourth one because if we had an else if t is less than 80, it would not be run either way because it's an else if, and this was already run. I'm getting an error. Misnamed variable. Alright, so now after this else, the if block here, we're going to update our variables. So shift some around. E is equal to D. D is equal to C. C is equal to the rotation of B by 30 bits. And then B is equal to A, and A is equal to temporary. Once again, just taken directly from the documentation. Now after the loop, after the, hold on, I messed something up. Make sure that your if t is greater than or equal to 16, make sure that block ends after you assign to WS. Because we need to calculate temporary and update these values no matter what round it is. This if statement here was only in place because we were setting the initial values. Honestly, we could just put this in here instead of doing that if statement. It wouldn't make a difference. You know what, we'll just leave it here, it's fine. Alright, so now that we have swapped around our values, did all that, we can continue on to the rounds, and then after all the rounds, we're going to add the constants back to our buffer. So h at 0 plus equals A, h at 1 plus equals B, h at 2 plus equals C, h at 3 plus equals D, h at 4 plus equals E. And that's it. That's SHA1. Let me go grab my water and then we can run and test this out. into main.c, and I'll include SHA1. Alright, so to test this, I'll just use one of the test strings from here, which will just be ABC, so we can try that first. So I'll comment out all of the stuff here for SHA3. So if we have an unsigned character pointer message is equal to ABC, then an unsigned character pointer hash is equal to null. Then we're going to say SHA1 context. So now we're going to be going through this new process of initializing a context and writing to it. So we're going to create the structure SHA1 context CTX. Then we're going to call the function SHA1 init context, pass in a reference to CTX. This will set up all the variables and stuff that we need. Then we have SHA1 update. So we're going to pass in the actual message. So we first pass in a reference to CTX1. Then the input will be message, and the length will be 3 for 3 bytes. Then SHA1 Digest from a reference to CTX1 to a reference to the hash. Or this should be CTX, sorry, not CTX1. Alright, then we're just going to print this out. So print character array. The array to print will just be hash. The length will be SHA1 output, and then we just won't put any spaces, and then we'll just free some values. So free message, free hash. Alright, so let's go ahead and run this. A999, blah, 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 blah. Is that correct? You bet your fucking ass it is. Yeah, it is. So that's good. Let's test another one. This one's a bit longer. It's 56 characters. But you'll notice that it still has the same output length, because once again, it's a hash function. It maps any value to, or not any value, but a set of values, maybe an infinite set, to a finite set of values. And we get 8498, and is that correct? Where is it? 8498, good. And you'll see in this test documentation here how we have 2 different blocks. So we'll process the first block. Let me just zoom in here real quick. So we have our message length, blah, 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 have the initial hex values. Then we do block 1, set the initial W values there. You see the padding starts, the padding will actually start in the first block. This 80, that's the start of the padding. However, we don't have enough space to write the 64-bit length, which would need these 2 integers here, because it's 8 bytes or 2 integers. So we need to pad a whole new block just to get to just to write the length. So we have that. Do the whole shebang on the rounds up to t equals 80. Get our h values and add the output to the initial h values. Then for block 2, it's the same stuff, but notice how the state is all zeros except for the last byte, which contains the length. So these last two bytes here contain the length. And then we run the function again, all 80 iterations, add the values to the existing output buffer to get our true output, which is yeah. A million repetitions of A. That's cool. Okay. I don't know if I want to do that. Good for you. No, let's try this out actually. Let me show you how we can use this update function to just go to run multiple or to concatenate messages. So let's just have our message be 5. We'll have it be, if it's 1,000,000 A's, then 100 times 10,000. So let's do this. So the message is equal to malloc 10,000 times the size of an unsigned character. We're going to set all the values to A. So mem set message, the value will be the character A, and the size will be 10,000 times the size of an unsigned character. And what we're going to do is we're going to initialize the context, and then instead of calling SHA-update once, we're going to call it 100 times. So for integer I is equal to 0, I is less than 100, I plus plus. We're going to call SHA1 update. The context will be a reference to CTX. The message is going to be the same message every time because we're just concatenating it. And then the length of this message will be 10,000, like so. And then we'll see how long this takes. Please work. Hey! Did it work? It worked. 34 AA, and that was actually pretty fast. 34 AA, all that good stuff. So you see how, even though we don't have a whole string that's 1,000,000 fucking characters long, we just have one that's 10,000. I mean, we can honestly make this even better. Let's do 100 A's and then do 10,000 repetitions, just to reduce the memory cost. This might take a bit longer. No, it was almost just as quick. But that makes sense because you're still going to be processing 1,000,000 characters, no matter if you take it 1 character at a time or 1,000,000 characters at a time, because you're only going to be calling the SHA1 function 1,000,000 divided by 512 or divided by 64 times. So yeah, that is pretty much how this new context system will work. I'm gonna implement it for the SHA3. I'll put the code on the GitHub, and I'll let you guys know when that works. But yeah, so that is pretty much all I have for you guys today. This was SHA1, and next time I think I'll be doing some algorithms based off of these hash algorithms, which will be pretty cool. So yeah, until then, take care of yourselves, enjoy your days, and I'll see you guys then. Have a good one.